Okay, we're going to look at a situation where we're looking at a projectile which is dropped, hits a surface, and then bounces. Now, it's important to remember in this particular situation that when an object hits a surface, then the reaction force is perpendicular to that surface. And therefore, the impulse caused by the impact will also be perpendicular to that surface. Consequently, when a ball bounces on a smooth plane, it will experience an impulse directed in the J direction. And consequently, we can apply the law of restitution, and we can multiply the approach speed by E and reverse its direction. But the speed in the I direction, because there's no impulse in the I direction, will remain unchanged. The key to solving this particular problem is ensuring that we actually have a neat and appropriate diagram. So what we have now is we have the traditional approach where we have the x-axis along the slope of the plane, and we have the y-axis perpendicular to the plane, and we need to chase the given angle into the problem. So what we have here is the situation where by corresponding angles and parallel lines, we now know that the angle here is equal to A. Because this dotted line and that line are at right angles, we know this is 90 minus A. And because this line here and this line here are at right angles, if this is 90 minus A, then the angle in here must be A. Hence, we've managed to chase that angle in. Okay, that's it's very useful. I'm going to rub out some of that stuff now because that's all done in your head under normal circumstances. And once you've chased the angle in, you've put an angle A in there. The other place from previous work where we know there's an angle A is in between this dotted line and the gravity, and that's also the angle A. And you have to read the question carefully because the question quite clearly says that the speed when the object hits the plane, the speed as it hits the plane is u. So the speed before impact, and we're going to do some resolving now, is we're going to be resolving this through the angle. So it's going to be equal to u cos of the angle A. Now that's going to be in the J direction. It's going to be negative. And if you resolve away from the angle, you're going to get u sine of the angle A in the J direction. Sorry, in the I direction. Now, I'm going to rearrange that so it's written in the usual format. So the velocity of the object just before it hits the surface, or as it hits the surface, is u sine A minus u cos A. And that's in the I direction, and this is in the J direction. I need to pause the video and think about that for a little while. Please do so. Now, we've already established that the impulse is in the J direction. Therefore, there is absolutely no change. Once it makes contact with the surface, there'll be no change in the speed in the I direction. However, we are going to apply Newton's law of restitution to this one and the J direction, the direction of the impulse, and we're going to multiply it by E. So the velocity of the object as it leaves the surface, the I direction, as we said earlier on, remains unchanged, but it is going to change direction in the J direction because it's bouncing back up again. and we're going to be multiplying it by the coefficient of restitution, which is going to be E. Now, if we read the question, we're told within the question that E is equal to 1/2. So therefore, we've now got U, the velocity of the projectile, as it leaves the surface, is going to be U sine A in the I direction, and it's going to be plus 1/2 U cos A in the J direction. And that's the only thing that is actually new in terms of this particular problem. Now, we can start our problem in the normal way. We're going to be looking now at U in the X direction, and U in the X direction can be taken from the statement above. It's going to be U sine A. The acceleration in the X direction, well, we have to look at this gravity, and we're going to be resolving away from this angle. So therefore, it's going to be G, and if you're resolving away from an angle, it's sine, so it's going to be G sine A. It's going to be positive because it's going the direction down the plane. And we're looking for the length of the first hop, which means we're looking for the range. So what we're looking for is the range, and traditionally we call the range R. We're going to be using a formula S equals UT plus 1/2 AT squared, and we're going to substitute in what we know. So R is equal to U sine A on T plus 1/2 on G sine A on T to be squared. As of now, we do not know the value of T. But what we do know is that this is a full motion problem. And because it's a full motion problem, we already know that the displacement in the y direction at the end of motion is equal to 0. So consequently, we can use this piece of information in order to work out time. Now, we know that uy from here, from the equation above, the u in the y direction, has been affected by the coefficient of restitution, and we know it's 1/2 u cos A now. We know the A in the y direction is, when we resolve it, it's going to be resolved through this angle, and it's going to be in the negative direction pointing downwards. So consequently, it's going to be G cos of the angle A, and it's going to be negative. The S in the y direction will be equal to 0, and we're going to be using S equals UT plus 1/2 AT squared in order to find the value of T. Sub in what we know, 0 is equal to 1/2 U cos A on T minus 1/2 G cos A on T squared. Taking out the highest common factor, we can take out 1/2, we can take out cos A, and we can take out a T. When we take out the 1/2, and we take out the cos A, and we take out the T, we're left with U. Similarly, when we take out the 1/2, the cos A, and one of the T's, we're left with GT. From this, we've got the traditional T is equal to 0, or GT is equal to U, therefore T is equal to U over G. We can now substitute this value, U over G, into the formula for range. So we have U sine A, and the value of T is U over G, so we can put that in, plus 1/2 G sine A on T squared. Now T squared will be U squared over G squared. So we've now got U squared over g squared. Now, you should spot that this g and this g will cancel, and we can factorize this expression. So what's the common factor? Well, u squared is a common factor, so we can bring that out on top. On the bottom, we've got g is a common factor, and we've also got sine A is a common factor. And what's left in the bracket? Well, we've taken out the u, we've taken out the sine A, we've taken out the other u, we've taken out the g. So we've taken out everything, then what's left is 1. On the other side, we've taken out the sine A, the u squared, and the g. So what's left behind is a half. And then when we tidy up, we're going to end up with r is equal to, well, 1.5 is 3 over 2 on u squared over g on sine A. And there's your expression for the range when we find the length of the first hop. Now, please study this example, make sure you understand it, and we're going to apply it when we're in the next lesson. So all I want you to do is study this example, make sure you understand it, and then we'll use the next lesson to apply it.